The next talk will be on quantum computing, and especially the entanglement issues that are related to cryptography and lots of other interesting future things. And with us today is Stephanie Wehner, a student at the CWI in the Netherlands and working on quantum computing. Welcome, Stephanie.
Well, good morning on this last day of the conference. This is going to be part 2, really, of my talk that I gave at What the Heck. But in case you weren't at What the Heck, this is going to be self-contained, so don't worry. I'm mainly going to talk about games today because, well, it's the last day of the conference. You're all just as tired as I am, and some more entertainment is probably good. OK. I'm first going to talk about qubits again, for the people who weren't there at What the Heck. And then I'm actually going to get to the part that I really want. Namely, I'm going to talk about entanglement, which is a very bizarre phenomenon. And I'm going to talk about something called action at a distance. And OK. Better? OK. And then I'm going to talk about why this is so special, what's the whole big deal with entanglement. And finally, I'm getting to the part that I really want to get to, namely playing games with entanglement. And finally, I'm going to talk about some applications in the area of quantum computing, and mostly in the area of quantum cryptography, referring back to my talk at What the Heck. OK. Probably many of you have by now seen this a few times before. Classical bits are just 0 and 1. But quantum bits have the funny property that they can actually be 0 or 1 at the same time in what is called a superposition. Only if you measure this state, you will actually collapse it to one of these things. I'm going to talk about more in a second. There's one important property to remember about qubits that makes them different, is that they cannot be copied. And in this talk, I'm not going to write 0 or 1, but I'm just going to use 2 directions, or 2 colors, you can even think of them, like red and blue. OK. I said that qubits can be in a superposition of, say, 0 and 1. And only if you measure the state, you will actually view a 0 and view a 1 with a certain probability. The state we set up here has the property that if we measure it, we will see a 0 with probability half and a 1 with probability half. That's all you really need to remember about qubits for this talk. And an important point to remember is that after we performed this measurement, the qubit is actually not longer in this state. It has actually collapsed to what we observed. So if we saw a 0, then this will be the state after the measurement. And if we observe the 1, then we'll be over here. OK. People at What the Heck have seen this slide before. I will not really need this much in this talk, but I will refer to it briefly later. So this seems pretty arbitrary. You can think of this as polarization directions of a photon, and it seems pretty arbitrary that we just choose, say, up and horizontal and vertical. We might, for example, also choose these 2 directions. That really doesn't matter. I will use this symbol to say that we measure in this basis. And what does that mean? You can think of it, maybe a lot of you have been doing some computer graphics, is for the purpose of this talk, you can think about if I measure in this basis, that means that I really project on these 2 directions. And for a different basis, I just have 2 different directions. This is pretty much arbitrary. I could have rotated this by 60 degrees, and we could still do exactly the same things. Because suppose now I have a qubit in this basis, say the diagonal basis, the red here, then I can, of course, re-express it in a different basis very easily. Because I can see, OK, it's like here, so I have a component of this part, and I also have a component of the lower part. Now, there's really only one important thing to remember for now, is that if I measure in the same basis, say if I have a qubit which is in a certain state, in a specific state, namely prepared in a 0 state, and I measure it in the same basis that I prepared it in, then nothing happens. It'll just remain unchanged. And likewise for any other different basis that I might choose. So if I measure in a different basis, suppose I now pick the diagonal basis, and remember that we could, of course, express it in terms of the other two directions. In that case, you can see, okay, I have what this means here is that I will observe this part with probability half, just what I have here squared. So in this case, if I measure it in the wrong basis, I will see a 0 with probability half and a 1 with probability half. And likewise for, say, the 1. And I can play this game with all the other states as well, of course. So for this one, of course, this is now a state in the horizontal vertical basis, but of course you can also see that you can express it in terms of the other bases. Okay. Now, at what the heck, I was talking about in the beginning of my talk about an effect called interference, which I'm not going to talk about now at all. Instead, I'm going to talk about something very bizarre, namely entanglement, which I hardly told you anything about at what the heck. So at what the heck, I only briefly mentioned that there is something called entanglement. So I'm going to use two players now, Alice and Bob, and they share a state, which means that they both have a qubit. You can think of this as some photon that they hold in their hand. And these two photons are in a certain state called an entangled state, which means that they're correlated in this way. Now, what does this mean? Now, at what the heck, I was saying that if Alice measures this state, she will observe red with probability half and blue with probability half. So this is, you can just look at this, it's just the same as before. So we have square root 1 over square root 2 here, so it's probability half. And just as before, measurement changes the state. So if Alice, for example, now, just suppose she saw a red when she did the measurement, then the state after the measurement will actually be just red, red. So in fact, if Alice sees a red, then she knows that Bob, whenever or how far away he might be, also measures this state, will exactly also see a red. She just knows this. And of course, you can play the same game with the other outcome. And Bob will, again, if Alice saw this blue, then Bob will always see blue as well. Now note, though, that actually we haven't transferred any information. Only Alice knows what Bob's outcome will be. Okay, so this is all I had said at what the heck. But you might argue, okay, maybe let's be a little bit more skeptical about what's going on here. I mean, it seems almost like, okay, we can just accept that this is the way it works and then all will be fine. But maybe let's think about this a little bit more. What's actually going on here? So we have these two particles, say Alice has a photon and Bob has a photon. But how does this actually happen? Why does this happen that if Alice measures her photon, then suddenly, even if Bob is, say, far, far away, actually Alice's measurement has an influence on his photon far, far away. So you could argue, so maybe actually there's really some communication going on. So you can test this. Let's just say we put Alice on Earth and we put Bob on Mars. And somewhere in the middle here, we put some spaceship which emits two photons. And we require that immediately upon reception, Alice measures it, and Bob does the same immediately upon reception. And then we ask him, okay, what were your outcomes? And we do that many times, and we'll in fact see that it's really true. If Alice sees red, then Bob will see red, and if Alice sees blue, then Bob will see blue. So if we accept the fact that there's no faster than light travel or also no faster than light communication, then clearly there must be something else going on here than just this particle somehow sending some information secretly outside of our view. Okay, so let's try something else. Now I've said that Alice has some chance of obtaining a certain outcome. It's not exactly clear what this means, right? I mean, in fact, it does not mean that, has this already been determined? Because maybe far away in the past, say this is nature, Nature has in fact already decided whether we're in the blue or in the red case. We just don't know it yet because we haven't measured yet. But really, it's there all along. Okay, let's presume that this is correct. It's really nice because, of course, if we assume this, that this must happen, of course, because it's been, say, blue all along, and once Alice measures, she just discovers it's blue, and of course, Bob once has to be blue as well. And exactly, if we do this many times, we will even observe the same statistics, because we say that, suppose for every such pair, nature flipped the coin, and with probability 50%, she says, okay, that was going to be blue, and with probability also 50%, she said it's going to be both red. So this fits what we see here perfectly. But let's examine this a little bit closer. So basically what would happen in this case is that nature beforehand already, with this particle, associates some kind of, I don't know, instruction sheet or cheat sheet where it says, okay, if Alice measures in this basis, then output this. And if she measures in this basis, then the output is going to be that. And likewise for Bob's particle. So you can think of this as this photon is just going to be enclosed in some box, which comes with some kind of instruction sheet, and that's all there is to it. Okay, so this is really no big deal, and I mean, there's nothing really mysterious about this. And so how do we know that this is the case, or maybe it's not the case? And like I said, I want to talk about games. So in fact, I want to look at this whole procedure now as a game. And of questions and answers. So we are now going to play against Alice and Bob. These measurement settings are going to be the questions. So we're going to play a really simple game where we just ask Alice and Bob 2 possible questions, 0 or 1. And likewise, there's only 2 outcomes for now, namely also 0 and 1. And the instructions that were given, say, beforehand by nature, you can see these as the strategies of the players. So they're going to say, okay, before the game starts in, they're going to talk to each other, and Alice says, okay, Bob, if I receive this question, then I'm going to say this, give this answer. And likewise, Bob, okay, if I get this question, then I'm going to give this answer. And they just agree on that. Okay, so we're going to impose some rules on this game. First of all, of course, we're going to tell the players what game we're playing in advance. It's maybe clear, but then before the players start, we allow them to go into a secret room and communicate all they want, so they can, in particular, generate these cheat sheets. And once the game starts, we don't allow them to communicate anymore. We can enforce this by, say, flying Bob to Mars and leaving Alice here on Earth. Okay, so in fact, here I want to play a 3-person game because it's easier to think about, but it's actually just the same thing. Only we have 3 parties now. And say we're going to put Alice on Earth, Bob on Mars, and I don't know, we put the cat in some spaceship in the orbit around Jupiter. And we're going to ask them questions. And they're really just going to be 0 or 1 questions. So we're going to ask Alice question X, the cat question Y, and Bob question Z. And we give them a promise, namely we're going to only choose questions thus that the sum of the questions mod 2 is just 0. May seem a bit obscure, but let's just assume we play this simple game. Can play other games too. Okay, and we're going to say that Alice, Bob, and the cat win if they can give us answers A, B, and C, such that the OR of these questions is going to equal the sum of their answers. Just set it up this way. And otherwise they lose and we win. Okay, clearly if we would have communication, then it's clear that they can win the game. They can tell each other which questions we ask, and then they can pick A and B and C in accordance with our requirements and win the game always. So let's make sure they can't communicate, but putting them far apart.